Hello, thank you so much for tuning into my YouTube channel. In this video, I want to talk about image registration using SIFT features. With the help of RANSAC, SIFT features are very suitable when it comes to image registration. The reason is they possess a very high level of invariancy towards many image transformations. To make it even more robust, we are going to also use RANSAC. And RANSAC is gonna help us identify the outliers in the features extracted from the images. Let's get started. Okay, let's get started on our tutorial on image registration using SIFT features and RANSAC in MATLAB. Image registration is the process of overlaying images of similar scene which have gone through different transformation because of being taken from different viewpoints at different times or by different sensors, or the same sensor but different filters. These are some of the examples of the images that need to be registered, especially Mona Lisa and the bridge on the far right. As you can see, these images need to be registered. There are two main approaches that have been chosen to do the image registration, and they are called area-based and feature-based approaches. In the area-based method, no features are extracted and the areas are matched up. But in the case of the feature-based method, first salient features of the images are extracted and then they are matched up. So that's a very big point to make, that these approaches, one of them just use area and the other one just use features, and we will tell you later on what effect it would have if you were to choose one of them as opposed to the other. In the case of the area-based method, usually control points are first detected or selected by the user, and then they are used to form a matrix transform between the images to be registered. While these methods are very popular, they usually lack a high level of accuracy, as the points selected are not some kind of features, which makes them incapable of invariancy to different types of distortion. Because that's the whole point about image registration. We need points that would be invariant to distortion, but with this method we don't have that plus, so the registration is not going to be as accurate. On the other hand, feature-based methods are comprised of the following steps. First is the feature detection, in which salient features like edges, corners, or blobs are detected. Second is the feature matching, in which the features in the reference and the test images are matched up. Third is the transform model estimation, in which a mapping function is estimated transforming the test image to the reference one using the matched up features between the images. Using this approach, features from the test and reference images with the most similar invariant descriptions are paired as the corresponding ones. The crucial point of all feature-based matching methods is to possess discriminative and robust feature descriptors that are invariant to all the assumed discrepancies between the images. Because again, that's the whole point about image registrations. The images would experience different process, so we want the features to be invariant to all those different processes. So using feature-based would enable us to have features that are invariant to all those transforms that in the first place have made different images for us. So diverse types of features have been utilized for the purpose of image registration, such as edge, corner, blobs, and so on. Here we're gonna use SIFT features, which stands for Scale Invariant Feature Transformation or transform. SIFT features have been utilized in different areas of machine learning, including object tracking, fingerprint verification, face authentication, image mosaicing, and so forth. SIFT features possess an invariant property toward different image transforms, such as scaling, rotation, etc., which makes it a great candidate when it comes to image registration. This is a very quick overview of how SIFT features are obtained, and we don't intend to go through it. Just an FYI that's how SIFT features are extracted from images. And the most important thing for us to know is they are invariant to most transformation that an image would go through. So it's going to make it a good, very good candidate for image registration. To make the matching process more robust when using SIFT features, RANSAC is also used to identify the outliers in the matching candidates. The outliers identified using RANSAC are set aside, and a matrix transform is then obtained between test and reference images features that fell in the inlier category. So this is a very good schematic example that shows if we have this threshold, these are gonna be the inliers, and these are the samples that are gonna be used later on to find the transform matrix between the images. So RANSAC would enable us to do that, but how it works is using this algorithm. First, select randomly the minimum number of points required to determine the model parameters, and then we solve the parameters using this randomly selected samples, and then we determine the number of points from the set of all points that would be fit within the predefined tolerance, and then we say if the fraction of the number of inliers, which is from number 3, over the total number of points in the set exceeds the predefined threshold tau, re-estimate the model parameters using all the identified inliers and terminate. So we just have to have the highest number of inliers possible using RANSAC, and this algorithm would enable us to do that. And then if this didn't happen, just repeat steps through 1 through 4. And as I said, this is a very good schematic way of showing how RANSAC works. And that's about it. Let's go to the coding part in MATLAB to show you guys how the codes work and to explain more the process. Okay, let's talk about the coding part of this video. First, I'm gonna be reading in the image, which is gonna be the unregistered version of Mona Lisa, and you guys saw an example of it. And then the image is gonna be turning into double, and then I need the size of the image, the number of channel, and the size of the image M and N. L is the number of channels, and the ref n refers to the channel to which other images are going to be registered to. For me, it's going to be the green channel, the channel number 2. So red and blue channels are going to be registered to this channel, and the size of the cube, and the output is going to be in img out 2. So if we go into the for loops for all the channels from 1 to L, L is the number of channels, I want the images to be registered to the green channel. So if I is equal to 2, which is the green channel, I don't want to register the channel number 2 to itself. So I'm gonna skip that I, which is I equals 2, and then I just need the image channel, which is gonna go from I1 and I3 channel, blue and red. And the channel is going to be put in here, and the first thing that we're going to do is to find the matching points between the image that is going to be registered to the reference image. The reference image is going to be the green channel, and this image is going to be the channel that is going to be registered to, depending on the value of I. For that, we use find matches 3, which is taken from this library, vlfit.org. And if you haven't downloaded and installed it, I highly recommend that you should do that and go and download this vlfit.org. And the latest version might be higher than this one, but just download and install it, which is very helpful. So this find match 3, it would find the matching points between the image to be registered and the reference image. Let's have a look at the find match 3. And you have to always put this run here. For me, this is the folder that the image is in, that the library is in, so I have to run it. And then after that, the SIFT features of the images are extracted and they are matched up. So that's how we find the matching points between the two images. So now we have the matching point, but we're going to find the inliers in the matching point. For that, we use RANSAC algorithm, which is referred to as inliers here. So this is the RANSAC algorithm. The number of iteration here is 20, and then the threshold value for which I specify the number of outliers or inliers is 10. So anything lower than 10 is going to be inliers, and anything higher than 10 is going to be outliers. The 10 would be compared to the value of error in the reconstruction of the samples. And inliers ratio, which refers to the inlayer lengths over the length of the whole samples, the number of all samples. And that would help us to find the highest number of inliers. So first we just choose a minimum number of samples, which is going to be 4 here, to fit a line, which all happening here. So we have matrix H here, and it's going to be reconstructed, and we have the Y. The Y is going to be estimated, and the Y we use the floor to just round it off to Y, and then that would be the predicted points. So we use these predicted points, and we calculate the error compared to the real value of points that we have from the matched points. And we would find the points whose error of reconstruction is lower than the threshold of 20, if I'm not wrong, 10. So anything lower than that is going to be in inlayers. And here we make sure that we have the highest number of inlayers. And yeah, so it's very fun and it's very robust. RANSAC is very robust to find the outliers, and it's going to help us to find the best matching points. So by the end of this process, by the end of 20 iteration, we come out of this possessing the highest number of inlayers. So after this, we have the matched points that are also inlayers from two images, from the image to be registered and also reference image. So we use CP2T form from a built-in function in MATLAB to predict the matrix transform, which is T form, and we use also similarity option in it, which contains the widest range of changes in the image. And then we use the matrix transform, and we transform the image to be registered to lay over the reference image, and that would be the output of these for loops. And we have two outputs, the blue and red channel, and which would be set here. And we have to make sure that the size of the cube would be here, and everything else would match this, otherwise the output would look a little bit funky. So the output would be turned back into an 8-bit image, and here using montage we're going to use the output registered image and the unregistered image of Mona Lisa. Let's run and see what happens. So as you can see, this is the unregistered Mona Lisa and this is the registered Mona Lisa using this method. And it just shows how robust this method could be, because SIFT features are very robust to changes, and also RANSAC would also make it even more robust. And we have in layers matching points, and we use them to register Mona Lisa, which has led to a very satisfactory results. That's about it. Thank you so much for watching this video. I hope you liked it and you've learned something useful. In one of the next videos, I'm gonna do the same thing. I mean, I'm gonna do the image registration, but using another types of feature, which are referred to as deep features. And I am expecting to have a better result, but we see in one of the next future videos. And if you liked it, don't forget to subscribe and also share it with your friends. Thank you again for watching the video. Have a nice day.